Hello everyone, and welcome to the first video on Chemistry 11. Before we begin, let me preface this course introduction by saying that you should probably look over the significant figures video. While in physics you can kind of get away with sloppy sig figs, you cannot do that in chemistry. We always follow sig figs rules to a T. The first thing you can learn aside from sig figs is the mole concept. Moles are highly important because they can be used to calculate many things. In fact, they're called the heart of chemistry. But what exactly is a mole? Well, in layman's terms, a mole is a specific number of a given molecule, atom, or particle. How much? Well, this is where we get introduced Avogadro's number. So Avogadro's number is equal to 6.02 times 10 to the 23. What does this number mean? Well, it means that for every 1 mole, there are 6.02 times 10 to the 23 molecules or atoms or ions, etc. In fact, it's not just restricted to any like subatomic particles. It could be 1 mole of computers could be 6.02 times 10 to the 23 computers. So how did scientists come up with Avogadro's number? It seems like a very specific number, and that's because it is. Well, Avogadro's number means something special, I guess. What it means is that, let's say you have carbon-12, okay? We know that carbon-12 is an isotope of carbon that has an atomic mass of 12 grams per mole. So scientists thought that if you had a sample of that element and the mass in grams was equal to the atomic mass, so in this case 12 grams, then what would be the amount of particles or atoms or ions inside of that sample? Well, the number they came up with was 6.02 times 10 to the 23. Now this doesn't just apply to carbon. Water, okay, H2O, has a molar mass of roughly 18 grams per mole. So if you had a sample of water that's 18 grams, then there would be 6.02 times 10 to the 23 molecules of water. So we talked a little bit about molar mass. So what exactly is molar mass? Molar mass is essentially the atomic mass, which is the large number under each element expressed in grams per mole. That's for a single element though. What about molecules or ionic compounds or just about anything that isn't a single element? Let's take water for example. We know that there are 2 hydrogen and for every 1 oxygen, okay, inside 1 molecule. And we also know the atomic mass of hydrogen is 1.00794 grams per mole. And then the oxygen has an atomic mass of 15.9994 grams per mole. So how would you determine the total molar mass here? Well, you just add them up. Okay. But there are 2 hydrogen here, so you multiply the hydrogen atomic mass by 2. Your result should be roughly 18.01528 grams per mole. And you'll notice that this number is very similar to this one right here. And that's just because they are the same molecule. So, are you lost yet? To review, Avogadro's number is 6.02 times 10 to the 23. And molar mass is just the atomic number of all the elements inside of an ion or a molecule or an element expressed in grams per mole. So with all of this, let's go on from here. As I mentioned before, moles are the heart of chemistry because they could be used to calculate many other quantities. The first relation to observe is the one between moles and the number of molecules, okay? So we know that 1 mole is equal to 6.02 times 10 to the 23. So if you want to determine the number of molecules, all you need to do is multiply it by the number of moles by by Avogadro's number. The second relation I want you to focus on is this one here. So if you have mass, and then below mass you have moles and molar mass. This forms like a little triangle here, and it's very messy, but yeah. So what this basically means is that if you're, say, looking for mass, okay, all you had to do was take moles and then multiply it by molar mass. So your equation here is mass equals to moles times molar mass. But what if you're looking for something else? What if you're looking for moles, for example? How would you determine moles from this equation? Well, moles is basically mass divided by molar mass. Moles equals mass divided by molar mass. Finally, the last thing you should know about moles is the concept of molarity. Molarity is basically concentration, and if you don't know what that means, concentration is, say you are in a room, the more people there are, the more concentrated the room is. So let's say in a given solution, the more of a specific element or particle or molecule, the more concentrated it is. And this is relative to moles. So molarity would equal to moles divided by volume. Because it's divided, there is an inverse relationship. So let's say the volume increases, then the molarity decreases. But if the moles increases, the molarity increases as well. So now that you know all of these, let's apply them to some problems. You may use the periodic table on the screen to help you with these questions. Before we begin these word problems, I think I should give you some tips on how to solve them. You don't have to adhere to these, they're not necessarily important, but they would be advisable to follow. So the first tip is that you should take things one step at a time. Oftentimes answer books and textbooks, they tell you to do multiple steps at a time, but those just give you more of a chance to screw up, and it's harder to find a mistake there. The second tip is you must always put unknown values on the left hand side. For example, if you are looking for moles and you're given mass times molar mass, you cannot write it like mass equals moles times molar mass. No, you can't do that. You have to write it in this form here, where the unknown value is on the left-hand side. So the third thing is that you should always have units in your questions. So even not just in the answer, but also in the equation itself. And you should always identify which element you're talking about. The fourth thing is that you should always have sig figs. I talked about this before, but it's not just a thing that you should do. You can actually lose a lot of marks by not doing sig figs, because Aaron is particularly picky about them. So with all that in mind, let's go over some of the questions here. So how do we begin? Let's go set up our equation first. So H2O molecules is equal to moles, and don't forget your units, so mole times 6.02 times 10 to the 23. So let's just go solve for this. H2O molecules, and we said 3 moles, right? So 3 moles times 6.02 times 10 to the 23. Your results should be 1.806 times 10 to the 24 molecules, but you want to remember sig figs. So if you remember sig figs rule, you remember that you only round to the lowest term. So if you remember sig figs rule, you remember that you only round to the term with the lowest amount of sig figs. So in this case, it's 3. Okay. So right now we have 4 sig figs, so we reduced down to 3. So it would be 1.81 times 10 to the 24 molecules of H2O. So the second question asks, what is the total molar mass of the following? Chlorine is just an element, so you can pretty much just pluck this off of the periodic table. So if you look in the periodic table, chlorine has a molar mass of 35.453 grams per mole. So the second one is magnesium oxide. So if you remember how we found the molar mass of water, we basically just took the atomic masses of them and they just added together. So that's the same thing we're going to do here. So let's go set up our equation here. So magnesium has an atomic mass of 24.3050 grams per mole. And you want to add that with oxygen, so that's 15.9994 grams per mole. So if you just plug this into your calculator, you'll end up getting 40.3044 grams per mole of MgO. Now let's do your third one. That's nitrate. Now nitrate is written as NO3 minus. So what does this mean? It means that there's 1 nitrogen atom for every 3 oxygen atoms. So let's go set up our equation again. That's NO. And the charges don't really matter, so this minus here, you can pretty much just erase it. So nitrogen has a atomic mass of 14.0067. And then again, oxygen is 15.9994, so we multiply that by 3. So your resulting molar mass for nitrates should be 62.0049 grams per mole of NO3 minus. So let's do phosphate now. Molar mass. So your results, so if you plug this into your calculator, your your sum should be 94.97136. But sig figs, remember? So oxygen only goes up to 4 decimal places, or actually 6 significant figures here. This sum has 7, so you want to reduce it. So 94.9714 grams per mole of PO4 3-. So if you think you understand this, you can give acetate here a chance. So if you think you got this in the bag, you can try doing acetate here. Okay, I hope that was enough time. So again, you want to set up your equation first. Now, acetate's a big one, but it doesn't mean that the process is any different. So there are 2 carbon, so 2 times 12.0107 grams per mole C. And then there are 2 oxygen here, 15.9994. And then there are 3 hydrogen, so 3 times 1.00794. So if you plug that all into your calculator, what you should get is 59.04402 grams per mole. But again, you want to be careful of sig figs, so your final answer should be 59.0440 grams per mole of acetate. So on to your next question. This is where things get a little more difficult, and it takes more than one step to actually solve for it. So this question asks how many water molecules are in 6 grams of water. So the first thing you want to determine is how would you get from mass to water molecules. You would first have to find the moles, and then you would have to find the water molecules, or the amount of water molecules. So, given mass, how would we solve for moles? Well, we would use this formula, right? Moles equals mass over molar mass. So the moles for H2O is equal to 6 grams over water has roughly 18.01528 grams per mole as its molar mass. So what would that equal? Well, your moles there would be 0.3330506104 moles. And don't apply sig figs to this yet. What we want to do is keep this figure here, and then we're going to solve for molecules. So we're going to take this, and we're going to apply this to the moles, and then we're going to multiply this by 6.02 times 10 to the 23. So what's the result here? So the result is roughly 2.00 times 10 to the 23 water molecules. And this is perfectly in line with the sig figs here, because there are 3 sig figs here and 3 sig figs here, so that's okay. So your fourth question asks you, how many moles are in 17 grams of chromium? This should be pretty easy. So we know that moles, to determine moles, all we need is mass divided by molar mass. Now, what is the mass of chromium? So the moles of chromium would equal to 17 grams of the sample divided by 51.9961 grams per mole. And remember, that's the molar mass of chromium. And your final answer should roughly be 0.33 moles of chromium. And that's after sig figs, of course. So, on to your fifth question. What is the molarity of 36 grams of aluminium in 4 liters of water? So, if you remember, molarity is moles over the volume, and that's in liters. So let's just go plug everything in. So now, how many moles are in the sample? Well, I guess we have to solve for moles now. Moles is equal to mass in grams over molar mass in grams per mole. So we have 36 grams of aluminium divided by the molar mass, and this is a long one, by the way, 26.981538 grams per mole. So if we punch that all into the calculator, we are given roughly 1.334245661 moles of aluminium. So let's just go plug that in here. So we have all that divided by 4 liters of water. It doesn't matter what it's dissolved into, it's just 4 liters. And your resultant should be a molarity of 0.33 m. So I forgot to mention this before, but molarity, the unit for molarity is capital M. Okay, on to your final question here. So find the percent composition of 10 grams of aluminium and 18 grams of sulfur. So percent composition, it's pretty self-explanatory. You just want to know how much of an element is inside of a given solution or resultant. So now you're given 10 grams of aluminum and 18 grams of sulfur. So the first thing you want to do is just add them all up together, add the masses together. So 10 grams plus 18 grams is 28 grams. Okay, so now that you're given the total mass here, all you want to do is divide it and then multiply by 100. So 10 grams over 28 grams times 100, and that's for aluminium, by the way, is equal to roughly 36%. So the percent sulfur is going to be 100 minus 36 equal. So that's roughly 64% sulfur. So that was the introduction to chemistry and moles. I hope this video was helpful and insightful. Anyways, I'll see you guys next time. Bye.